Buenos días, lamento el ruido. El municipio de San Nicolás ha decidido cortar césped debajo de mi ventana, pero por suerte vamos a estar mayormente en pizarrón, entonces voy a poder alejarme un poquito de la ventana. Les recuerdo que ustedes me pueden indicar si o no queda claro lo que yo estoy diciendo usando los votos que habíamos platicado antes. O sea, como ustedes ya tienen su matrícula con el bot y su correo en mi sitio web, pueden usar el Discord. Le puedes o escribir en el channel exclamación voto y luego el color que tú quieres votar, o tú podrías usar un mensaje directo enviándolo al MathBot y ya no necesitas poner la exclamación, nada más puedes poner cosas como voto amarillo, voto verde, etcétera, para decirme cómo va. Hoy vamos a estar platicando de algo que es muy importante en el análisis de algoritmos, pero para entrar a eso, pues hay que averiguar que si todo el mundo sabe qué es un algoritmo. La palabra algoritmo refiere a un método de solución y en los casos típicos nosotros estamos suponiendo que se trata de un método de solución que es determinista y sistemática. ¿Tienen que ver esto? Hay una pata. Hola, pata. Bueno, vamos a dejar la pata en la cámara. Entonces, un algoritmo simplemente refiere a que yo tengo una secuencia de pasos establecidos que yo voy a seguir de cierta manera para llegar a una solución. Entonces, nosotros ya hemos visto varios algoritmos. Por ejemplo, en la tarea anterior usábamos el algoritmo de Floyd y Warshall para determinar las distancias entre todos los vértices de un grafo. Y ese algoritmo lo que hacía era 3 ciclos for. Para cada vértice I, para cada vértice J, para cada vértice K, hacíamos ciertas cosas. Entonces, yo tengo un ciclo for que visita las n vértices, dentro de ello otro que visita n vértices y dentro de ello otro más que visita n vértices. Yo tendría un algoritmo que ocupa una cantidad cúbica de pasos, porque tengo el for que va por los n, un for que va por los n y un for que va por los n. Entonces yo tengo un n cúbico como la cantidad de veces que yo tengo que repetir lo que viene dentro de ese último for. Y como lo que viene dentro de ese último for ya no depende de cuántos vértices tengo, sino siempre es una misma cosa constante, nosotros diríamos que el algoritmo de Floyd-Warshall tiene una complejidad asintótica, que es el cubo del número de vértices que yo tengo. Gracias, Raya. Muy útil. Entonces, hoy, en lugar de hablar de algoritmos específicos, vamos a acostumbrarnos a esta notación que significa cuando yo pongo O's caligráficas grandes en frente de nombres de funciones. Para la primera tarea, vamos a aprender una regla muy útil y muy sencilla, pues más bien la primera pregunta de la cuarta tarea. Cuando yo tengo un polinomio, polinomios son las madres esas que aprendieron en secundaria, donde yo tengo, por ejemplo, 3x elevado a 4. Y ahora, como estamos hablando de algoritmos, vamos a brincar negativos. Vamos a suponer que yo tengo 2x cúbicos, 15x al cuadrado, 2x y luego una constante 13. Cuando yo tengo una expresión que es un polinomio, yo estoy interesada en su complejidad asintótica. Fray, ahora no se ve nada por tu pata. Pata. Gracias. Bueno. Pata. Esta pata. Gracias. Ok. Entonces, cuando yo tengo un polinomio, su complejidad asintótica, la tasa de crecimiento de esta función, el que tan rápidamente crece. ¿Y a qué refiere con crece? Si acá, esta es mi función f de x, si en eje vertical voy a poner cuánto vale y en eje horizontal voy a poner cuánto vale la variable, el crecimiento refiere a que cuando yo voy aumentando x, a qué tasa va subiendo el f de x. Y entonces algunas funciones puede ser que crecen muy light, otros podrían crecer lineal con diferentes pendientes, otros podrían tener un crecimiento exponencial, por ejemplo. Entonces lo que nosotros queremos saber cuando trabajamos con algoritmos no es tanto cuánto vale la función, sino cualitativamente cómo se va a comportar, y ni siquiera nos importa al inicio, nos importa a lo largo. Porque, por ejemplo, este algoritmo acá se vería súper bien para pequeños valores de x, pero a partir de un momento, pues se pone mal. Mientras otro acá se ve peor al inicio, pero a lo largo va a ser mucho mejor, porque este se dispara y el otro se mantiene. Entonces, lo que nosotros estamos buscando es saber qué tan feo se pone a lo largo el comportamiento de la función cuando yo sigo aumentando el valor de la variable. Y si nosotros pensamos en términos de x yendo poco a poco hacia infinito, nosotros podemos observar que en un polinomio como esto, los términos de menor grado tienen menor peso. O sea, más grande que se ponga x, menos nos va a importar que aquí hay un 13 al final, porque este 13 no depende del valor de x. Todos los demás, si x vale 1000, todos los demás términos valen un chorro, pero 13 sigue valiendo 13. A 13 no le importa si x vale 10 o 100 o 1000 o 10.000 o 3 millones, 13 sigue siendo 13. Entonces, eso significa que para la complejidad asintótica, cuando yo no estoy interesada en la función tal cual, sino yo estoy interesada en su complejidad asintótica, ya que hay términos mayores presentes, la constante no importa, lo puedo quitar, lo puedo eliminar por completo, porque está dominada por los demás términos. Los demás términos crecen tanto más rápido que no importa la constante. Y ahora vamos a repetir el mismo razonamiento. Si x va creciendo muy rápidamente, el x elevado a 4 crece un chorro, muchísimo. Cúbico también, mucho. Cuadrado, bastante. 2 veces x, no tanto, porque es nada más la x. O sea, si pensamos nosotros que x valga 10, bueno, entonces 2x vale 20. Y si x vale 100, pues entonces 2x vale 200. Pero ¿qué le va a pasar al cuadrado? El cuadrado del 10 ya vale 100. Y el cuadrado del 100 vale muchísimo más. Entonces, este término domina a este, de la misma forma que este dominaba a la constante. Este crece tanto más rápidamente que este ya no nos importa. Y de la misma forma, la 3 en el exponente domina a la 2. Y la 4 en el exponente domina a la 3. Entonces, en realidad, el único término que me importa en un polinomio al determinar su crecimiento asintótico es aquello que tiene el mayor exponente. Los demás no tienen ninguna importancia. Entonces los puedo quitar todos los demás. Por otro lado, este múltiple constante tampoco importa. Al cómo crece la función es igual si es 1 veces x elevado a 4 o 10 veces x elevado al 4. Es nada más una constante como que multiplicativa. Tú nada más estás como que moviendo la misma forma de la curva multiplicándola. Pero la esencia de la curva no cambia. Multiplicar por una constante no hace ningún cambio esencial a cómo se comporta. Sigue siendo un x elevado a 4 multiplicado por alguna cosa que no nos importa. Entonces, esta es la maravilla de la complejidad asintótica. Cuando alguien te pide sacar la complejidad asintótica de un polinomio, tú te vas a deshacer de todas las constantes que están multiplicando los términos y también te vas a deshacer de absolutamente cada término que esté dominado por uno de mayor grado. Entonces, con esto podemos contestar la primera pregunta de la cuarta tarea. Pinta que Rogelio tiene alguna bronca con el audio, pero yo no sabría decir por qué. Vamos a echar un vistazo a este acá, que es mi primera pregunta de la tarea 4. Les quiero recordar que todo el mundo tiene una pregunta ligeramente diferente, pero ya sabiendo qué estamos haciendo, debería ser fácil. Si están teniendo un desfase de audio y video, puede ser que funcione recargando a su Twitch. Twitch ha tenido problemas últimamente desde que tenían un link de su código fuente, entonces no sé si esté funcionando todo como debería. O también puede ser que esté batallando algo por el güey que está cortando césped debajo de mi departamento, pero espero que pronto vaya a tomar un break. Intentemos aguantar. Ok, entonces acá tenemos la primera pregunta. Nos pide justamente la complejidad asintótica, nos pide simplificar esta expresión y nos damos cuenta que este es un polinomio. Es un término más término más término más término. Tengo una sola variable que se llama x. Entonces yo ya sé que estos múltiples no importan. Este 5 no importa, este 6 no importa, este 7 no importa y este 5 no importa. Además, esta x domina al constante, entonces el constante se quita. El cuadrado domina al 7x, entonces este término se quita por completo. Entonces lo único que me queda es este último término mayor exponente acá, el 5x al cúbico. Y como el 5 no importa, lo único que me importa es el x al cúbico. ¿Y qué me dice? Escribe tu respuesta en el formato O mayúscula, paréntesis, X, gorrita y D con el exponente adecuado. Mi exponente que representa mi complejidad asintótica, entonces es la 3, porque es una cúbica. Entonces yo escribo, tú puedes nada más copiar y pegar de acá si no sabes hacer la gorrita, o paréntesis X gorrita, cualquiera que sea mi mayor exponente, cierro paréntesis y califico. Vótenme verde, por favor, cuando hayan contestado correctamente esta primera pregunta. Entonces, aunque suena algo complejo, es una cosa profundamente sencilla cuando se trata de polinomios. Cuando tú ves un polinomio, descartas los términos que no tengan exponente mayor y después te deshaces de cualquier múltiple constante que esté acá enfrente. Ellos se van y lo que queda es tu complejidad asintótica de ese polinomio. En la segunda pregunta, nosotros tenemos una situación donde estamos comparando múltiples diferentes funciones. Y ahora fíjense que no importa cómo se llama la variable, se puede llamar X, se puede llamar N, se puede llamar Manuel, se puede llamar Juanita, no one cares, es nombre de una variable. Entonces voy a escribir en pizarrón las funciones de mi tarea, tú vas a ver las funciones de tu tarea y los escribes en tu libreta para ir paso por paso haciendo lo mismo. Vamos a brevemente ver las mías. Entonces, las mías se ven así. Tengo f de n, g de n y h de n. Ustedes también van a tener, pero vamos a tener diferentes números, diferentes cosas acá en cada función. Y ahora vamos a intentar entender qué significa este texto que está intentando representar una función. Entonces, mi f de n, ¿qué dice? Dice que tengo una raíz cuadrada. SQRT viene de square root. Tengo una raíz cuadrada y luego las paréntesis indican que está dentro de la raíz. Tengo una n elevado a 4 en mi raíz cuadrada. Seguido a esa raíz cuadrada tengo un n al cuadrado y luego tengo un logaritmo de 5n y ese va a venir elevado a 5. Bueno, ahora nosotros que estamos trabajando con complejidad asintótica, pues ya sabemos que este 5 no nos importa gran cosa, entonces no vamos a fijarnos mucho en eso. Y si sabemos algo de logaritmo, vamos a saber que este 5 tampoco nos importa. Vamos a hablar de por qué ese 5 no nos importa. Si tú tienes el logaritmo de x elevado a y, esto es lo mismo que y veces el logaritmo de x. Voy a tomar foto. Propiedades del logaritmo. Imagino que en algún momento en preparatoria sucedió esto. Si lo ignoraste por completo, pues puedes ver un video de Khan Academy o alguna cosa así sobre el logaritmo. Estoy bastante segura que también viene en algún lado del libro de texto. Entonces, este es un hecho. Cualquier logaritmo se porta así. Logaritmo de alguna cosa elevado a la potencia es esa potencia multiplicando el logaritmo de la cosa original. Entonces, eso significa que cuando yo veo un 5 acá enfrente, esa es una constante multiplicativa. No es en realidad un exponente, porque yo podría moverlo acá enfrente. Entonces, cuando yo estoy viendo esta expresión acá, nada más tengo que pensar que hay un log de n, porque ninguno de estos 5 en realidad importa en la complejidad asintótica. Entonces, yo sé que yo tengo raíz cuadrada de algo, n elevado a algo y un log de n. Antes de proceder, vamos a simplificar. Si yo tomo una raíz cuadrada de n elevado a 4, recuerden que la raíz cuadrada es tomar una potencia de mitad. O sea, si yo tengo raíz cuadrada de x, eso es x elevado a la mitad. Y si yo tengo x elevado a, que luego está elevado a b, esto es lo mismo que x elevado a multiplicando a b. Por lo cual, si yo tengo una raíz cuadrada de n elevado a 4, ese es un n elevado a 4 elevado a la mitad. Y eso, por esta propiedad, es un n elevado a 4 multiplicando la mitad, que es un n al cuadrado. Tomo foto otra vez. Hoy ya suena más a matemáticas, ¿verdad? Tomo primero foto de las dos propiedades. Oh, Rogelio, I'm so sorry. I keep forgetting. We really should be doing this in English. This is entirely my fault. I forgot. You guys need to tell me when I do this. Just need to tell me because I really profoundly don't care. Okay. Thank you, Rogelio. Thank you so much. Okay, so we have these two properties. We have the square root actually being an exponent, that's 1/2. We have the exponent on an exponent being the multiplication. And hence we know that we can simplify the square root of n elevated to the 4th power as an n squared. So this thing here, this is actually just an n squared. Getting rid of the properties that I already took a picture of. And for all of those who are disappointed for Rogelio's observation, just come back at noon. This is supposed to be in Spanish at noon, but this is supposed to be in English for you guys because you guys are special. Okay, so now I have an n squared multiplying an n squared. Another thing you learned in high school is that when you have something elevated to a power, and that's multiplied by something elevated, that same something elevated to another power, you actually get the sum of the powers. Taking a picture again. So that means that all of this stuff I have here is essentially, I'm going to use the approximation because I'm going to get rid of these 5s. This is essentially n to the 4th power log n. That's what's really going on in my Fn. Let's reset the votes and check if we're fine. Please vote green if you understand where this part comes from. That why this thing here becomes this thing here. Vote green for this first. Please vote red if you have a question, and yellow if you think you can figure it out over time, but it's not clear to you right now. Just this part, that this part here actually means this. That's what we're voting on. 4 people understand. Let me move my camera so that the votes aren't on top of the thing. I think I moved it the wrong way. There we go. Okay, one person has a question. Let's look at the question. No, Ulysses, don't know. We're not doing yours yet. We are trying to make sure everybody knows why this happened to me. When everybody understood this one, we're going to look at my G and my H, and then we talk about yours. I need to know that everybody knows why I simplified it this way. Okay, we seem to be okay with that. And also that this 5 here is not interesting to us because it's a constant multiplier, and that this 5 is actually also a constant multiplier. So I don't really care of either one of those. So that means that this part it's not the same. This one is exactly the same. This one is just asymptotically equivalent instead of exactly the same. So these 2 things are exactly the same. These 2 things are roughly the same. Okay, let's look at Gn. My Gn. Where is my Gn? Over here. My Gn, I have exactly what we just wanted. I have a square root of n to the 5th power now. And then I have an n to the 5th. And then I have a log of something. I have a log of 2n squared. So we're going to do the same reasoning here that we did on the previous one to simplify it in a similar fashion. And the same exact rules we used. So what we learned is that when I take a square root of something that has a power, I'm actually dividing this power by 2. So what I get from here is an n to 2.5. And that, when I combine it with the other n to the 5th power, what I get is 2.5 plus 5. So I get an n 7.5. And this thing here, it's again just going to be roughly a log n. So this one halved plus this one gives this one. Resetting the votes. Please vote green if you understand where this 7.5 is coming from. While you guys vote, I'm going to write my h of n. That's going to be a square root of n squared. And then I have an n to the 5. And then I have a logarithm of 4n cubic. I would like to point out that if you guys have edited your Discord username, you need to send your student ID again to the bot. Because anytime you change your Discord username, the bot forgets who you are. Because the only thing it's remembering is this Discord username has this student ID. So if you change your Discord username, he's like, hey, this is a new person. It doesn't get a notification that you've edited your username. So you need to let it know. Okay, apparently everybody understood where the 7.5 came from. So now we should easily be able to work with the last one. Here we're just going to get n to the 6th and then a log n, and this is going to be approximately. So now we can actually read the question because we have simplified the functions. Now, what is the homework question saying? It says, which of the following three functions is the slowest to grow in terms of asymptotic growth? So slowest to grow means we'll have lower values when n goes high. So all of them are multiplied by a log of n. So that's not really something that's very relevant to me because they all have it. Where the difference is in the exponent. So if I want to know which one of these is the slowest, I need to fixate on their differences. And the smaller the exponent, the slower the growth. Because if I put a large exponent, the function kind of shoots off. And if I put a smaller one, it shoots off like less drastically. So of my three functions, the slowest is this one because it has the smallest exponent. So for my question 2 in homework 4, what I am going to be responding is Fn. Let's look at the homework question again. The part where I actually included the answer. So now it says that you should write x parenthesis n parenthesis. Don't put these quotes. Using the letter in place of x that corresponds to your slowest function. So my slowest function was an f. So I wrote an f parenthesis n parenthesis and I graded. If in your question you have the same situation as I do, one of the exponents is clearly smaller than the others, then this should be really easy to respond because you just look at what's the lowest one and you vote that one. But sometimes you have several that have the same exact value. So I'm going to return to the whiteboard to help those people who actually have the same exact value. So I'm going to modify mine to pretend I had the same exact value. I am going to pretend that I had here an 8, because if I have an 8 here, then I get a 6 here. So when I do this pretense, I actually now have the same exponent in these two. I'm just going to ignore the center one because that can't be the slowest because it has a higher exponent. So now if I have these two that have the same exponent, how am I going to now know which one is the slowest? Technically, they are equally slow. But if I really want to know what the difference is, then I need to look at these numbers here. Because remember, this number here is going to go outside the logarithm. Whereas the other one, this 5 and this 4, these ones stay inside the logarithm. So if you're inside the logarithm is acting on you, and the logarithm is a very slow-growing function, so it does very little. But if you're actually outside, you're actually multiplying this whole thing. So that means that this thing here, it's essentially similar to 5 times this thing. Whereas this one here is essentially similar to 3 times this thing. So when I have the same exact exponent, the lower one in growth is going to be the one that has a lower one here as the power to the n inside the logarithm, because that's actually going to jump out to multiply the rest of the expression. And if those are the same one too, then you need to look at the number that's inside the logarithm. Kind of like the more equalities you have, the deeper you dig in to try to find the difference. I'm also going to show you how we could do this in Python, because that's actually what my computer is doing when you grade your homework. My computer is evaluating all of the three functions with very large numbers of n and checking which one's given me the smallest number. So let's do that. Let's go look at my functions again. And let's get a terminal. Slightly larger, please. There we go. And going to Python. So let's make functions. I'm going to make an f of n. But before I can do this, I need to bring the math functions. From math, I need to bring a logarithm and square root. Then I can define my f of n. What's my f of n? I'm going to return the square root of n to the fourth multiplied by n squared multiplied by a logarithm of 5 times n elevated to the fifth power. That's my f of n. Then we could evaluate it. I could ask, like, what's f of 10? What's f of 100? What's f of 1000, etc. So then let's make a g of n. That one will return a square root of n to the fifth. It's going to be multiplied by n to the fifth, and that's going to be multiplied by 2 log of 2n squared. I'm so bad at typing. So now g of n, what did I do? Oh, g of 10. G of 10 would be like this. G of 100 would be like this. And g of 1000 would be like this. So now I could just test stuff like which one is smaller. Like, is it true that f is smaller than g when I evaluate it at 10? Is it true that it's smaller if I evaluate it at 1? If it's true that it's smaller when I evaluate it at 100? And remember, asymptotic means for large values. So it doesn't matter if with a small value, f isn't smaller. As long as when I keep going to larger, f remains smaller. Let's make my h as well. H of n is going to be a square root of n squared. I'm multiplying that by n to the fifth, and I'm multiplying that by a logarithm of 4 times n cubed. So now I can make stuff like for, let's say, power in range, let's go up to 20. No, 20 is a lot. 12. I could put that n is going to be, for example, 2 to the power. And then I could print stuff like, oh, come on. I wanted to print a formatted string where first I want to put the f of n, then I want to put a tabulator, then I want to put the g of n, then I want to put another tabulator. My R key is stuck, it keeps trying to do R's. Come on, don't buy Razer keyboards. Razer keyboards are horrible. Then I could take h of n, and then we could end the line there. So I can make this little table where I can print the values of f, g, and h for several different values of n while it keeps growing. So now if I want to know which one is the slowest, I would be interested to know which of these numbers is the smallest. It's kind of easy to tell it's going to be f, because these here, these are already in scientific notation. These are huge numbers, and this one isn't in scientific notation yet. If I don't want to look at the number, I just want to know what one is smaller, which one's the smallest. And I already have a hypothesis. I think it's f. I could do stuff like, instead of printing that, I could just print whether f is smaller than g, and also whether f is smaller than h. Now, this is a little bit inefficient because I'm calculating the value for f twice. But it's pretty easy to see that even though in the beginning f wasn't bigger than they are, for large values, f seems to be systematically smaller than they are. So we could try this with a bigger number. And yeah, it seems that systematically f is the smallest of my three functions. So let's give you guys a screenshot of what I'm doing up here, how I'm defining these functions. I'm just going to put the 1 for the f and an example of how I evaluate it. Here's my Discord. And then I'm going to give you guys a screenshot of maybe this one here. After I've defined the three functions, I could just print some of their values. There. So if any of this seems confusing to you, I'd like to remind you that there is a little video of doing this step by step, so that it's a little easier to go over it. And now I would really like us to go over some like actual more theoretical observations here. I want to go over a tiny bit of the Wikipedia page with you guys. I would like to remind you that we are not discussing like any mathematical functions whatsoever. We're interested in functions that are describing how many steps an algorithm needs to take. So the algorithm will never be taking a negative amount of steps. And we're also assuming implicitly here that the more data I give it, the longer it's going to take. So like if, let's say I'm sorting an array, I'm putting in increasing order, the numbers in an array, I would expect that if I need to sort a 20 element array, it's going to take more time than a 10 element array. So mathematically, this means that we have functions that are non-negative, and we're also supposing that they're monotonically increasing, as Habib's pointing out on Twitch, meaning that they either remain the same or they increase in value. They're never going down. But let's look at the Wikipedia page because it looks a little bit intimidating at first, but it's really saying things that we are now familiar with. So we can try to get used to reading mathematical looking things together. Okay, so let me zoom in a tiny bit. So this thing, it's called the big O notation, meaning that I'm putting usually a large calligraphic O, and then I'm putting a function in between. And this limiting behavior of function means what happens when I put large numbers in it. Like how is it behaving? Which way is it growing? And the part here, the argument tends towards a particular value or infinity. The argument means the variable I have there, like my x or my n. And then it's mentioning that this can also be called the Bachmann-Landau notation because of the dudes who introduced it. And as we said, this is used to classify algorithms according to how much time they take when I give them larger inputs. Like, for example, in graph theory, when the number is larger. This is also used in other parts of math, but for your studies, you will usually be using this for how long does an algorithm take or how much space does an algorithm require. And the usual examples, like the ones on the study material, we have a function of our interest, like the red one here, the f, and then we have another function g, and what we're trying to argue is that f will never be larger than some multiple of g, that there exists some multiple of g. It's a little bit inconsistent here because it's called the multiplier is a little c here, and the multiplier is a big M here. And the point is that no matter how far to the right I keep going, the red line will never go above the blue line. And if it would go, I would just try a larger multiple. And if such a multiple exists that f can never go above g, then we say that g is an asymptotic upper bound to f, meaning that f is limited from above by this g. There are also several other notations, like since this is limited from above, we could also have a limited from below or limited from both above and below. And there's practically a textbook worth of stuff here talking about the properties of this definition. And we usually use the computer science version that we're supposing that these are functions that take integer values and that they never ever give negative values, they only give positive values. And we're also typically assuming that the functions might be in a different order in the beginning, but from some sufficiently large threshold n0 onward, the order is going to be the asymptotic order. Like it doesn't matter if they kind of like shuffle up and down in the beginning. Like it doesn't matter if the red goes above the blue here in the beginning, as long as from some critical point, some specific size, which is here the x0 onward, it never goes above the blue one again. There are examples here. There is an explanation on how and why we use this. There is also a graphic similar to what we have in our study material to what do the growths of different functions look like. There's a little bit of properties of how this goes. The sum property is the one that we were using when we were talking about the polynomials. We could do this if we had more than one variable, like x and y or n and m. That would be very helpful. And we often have to do this with two variables when we work with graphs, because we have n, which is our number of vertices, and m, which is our number of edges, and those are both very relevant. Some people try to put that f is equal to the O of G to say that f belongs to the growth class of G. I don't like this. I think it's more precise to use the belonging symbol, because essentially this big O thing, it's essentially a set. The set of all the functions that have the same asymptotic growth. So it's a bad thing to say that a function is equal to a set. It's much more precise to say that the function belongs to the set. Then there are terms of how do we call this. If a function grows like a constant, we say it's a constant function. If it grows as a log of n, we call it a double logarithmic function. If it grows as a log of n, we call it a logarithmic function. Polylogarithmic would be if we're taking a power of the logarithm. Very important to put the parentheses because it's not the same thing as the log of n to the c. Quadratic is when there is a power of 2. Polynomial, when it's some arbitrary power. Exponential, when it's a constant elevated to the variable, and it's a factorial growth, which is when we have a factorial of n inside. Then the little o's are a different notation that we could also be reading. Basically, f is in little o of g means that the g of x is much faster in growing than f. Big omega is the thing that I was mentioning before. That's kind of like bounding from below, but there are two different definitions that people use in the literature, and those are not really compatible. So you can read this if you want it. In computer science, Knut is usually a bit of an authority, and he's using it for a different property, kind of like meaning that f is bounded from below by g if g is bounded from above by f. And this is kind of the one that I personally prefer in computer science, the properties of that. And then some ways of how to read these notations. The theta notation is very nice. The theta notation is when you have both the big O and the big omega, meaning that a function bounds the other one from both above and below, different multiples. It kind of like squeezes it into a sandwich. And this is all the reading that you could do. But for the purposes of passing this class, the things you need to remember are the things that we just did in the homework, meaning if someone gives you a polynomial, you will discard all the lower power terms and you will discard all constant multipliers. If someone gives you two functions, you will simplify those two functions to figure out which one grows faster and which one grows slower, and you're always going to carefully read the question. For the final exam, we're actually going to be having to memorize a little bit of things. I'm going to see if I can find the example. No, this is not the one I want. I can't remember the, let's just go to the examples as such. Es porque estoy escribiendo en inglés. No va a encontrar nada. The bot isn't bilingual. Let's go look at the example for how to prepare for the exam. Okay, so during the second half of the course, we're going to run into many different problems and we're going to run into many different algorithms. Last week, we were looking at this one, distances in a graph, and we were solving it with the Floyd-Warshall algorithm, and that was a cubic algorithm. So I might ask you in the final exam stuff like, what's the worst case complexity of the Floyd-Warshall algorithm? And you would pick out the option that it's cubic. Or I could ask you, what's the algorithm that you use to find distances in a graph? And you would say Floyd-Warshall. Or I could ask you, what's the Floyd-Warshall algorithm used for? And you would say, it's for finding distances in a graph. I could also ask you, what's the input to the Floyd-Warshall algorithm? Like, what data do you need to give it? And you would say, the graph. Or I could ask you, what's the output of the Floyd-Warshall algorithm? And you would tell me, that's the distances. So I made you guys this little table here so that anytime we're learning about a new problem, a new algorithm, you can look up what's the asymptotic complexity for the worst case. And you can kind of like try to develop some kind of intuition. Don't memorize the whole thing of what algorithms go with which problems. I personally hate this. Like I hate learning some dead dudes' names. I really struggle remembering which one is prim and which one is Kruskal when there's two algorithms for the same exact thing. So I kind of wrote little tips here of how the algorithms operate. So anytime we face a new problem or a new algorithm and you're thinking, will this be on the exam? Just go look at this little table. If it's in this little table, it will be in the exam. So what are we going to be doing next week? Next week, we are going to be finishing the fourth homework. And let me show you guys what awaits us there. I should have just pressed this button, really. Discrete Math. Next week, finishing homework 4. It won't be as theoretical as today because we just really needed to cover this concept, what is asymptotic complexity? And when we already know it, we can get into more algorithms for more problems. So we're going to be doing next week, we're going to be dealing with two very important computational problems. One of them is called the knapsack problem. In Spanish, it's problema de la mochila. We're going to have a code that we're going to use to work with that, to solve it. And we're actually going to need to use Python. This is not something you're going to be able to do by hand. So please install Python. If you haven't been able to, please stick around today and I will help you to. And then questions 4 and 5 have to do with a different problem. That's going to be a graph problem. It's called the maximum flow problem. And what we do in the maximum flow problem, it's kind of like if you have, let's say, a sewer system for draining rainwater when it rains on the streets, and you need the rainwater to go to some river or some deposit. You don't want it to be flooding the streets. You're kind of interested in the capacity that the system has for passing the rainwater from the origin to the destination. And in preparation to be able to do these three things, I am going to remind you guys where the codes are. So please, everybody, install Python for next week, and you can go play with the codes that are in the repository so that you'll be better prepared. The codes that we need for the homework assignments are in the homework folder. And next week, we are going to be first working with the knapsack problem, which is here in this file. I'm going to copy you guys the direct URL. This code here. You don't need to modify the algorithm. We're just going to be working with the data in the beginning and the restriction of the problem. I will explain all of this next week. And then for the questions 4 and 5, we're going to be working with the Ford-Fulkerson algorithm for the maximum flow. I have no idea why I'm looking at the changes for it. Homework, Ford-Fulkerson. It's here. It's going to have subroutine for augmenting paths and then the algorithm itself. And we're only going to be modifying the end part again, which is the problem instance and the parameters, the source and the target vertices that we're going to be working with. So if you're uneasy about working with Python, or if you're curious to get a head start, you can play with these codes on your own. And there's also the video for homework 4, the same one that has the questions 1 and 2. It's going to continue with questions 3, 4, and 5, all in the same YouTube video. So let's make a little poll. Please vote green on the poll or on the stream if you already completed correctly the first 2 questions of homework 4. I'm going to make a second poll. If you already have a Python installation, please vote green on the second poll. If you do not have a Python installation, if you cannot use it locally, then you should interact with this website that I just linked, like for Natalie, where you can use Python online. If you think you should be able to install Python, but it's for some reason not letting you, the easiest thing might be to meet me on the voice channel, share your screen, and we're going to try to figure out how exactly to make it work. But you can also use an online site. I'm going to show you briefly how to use an online site to work with the codes. Let's use the one for the knapsack problem that I just linked. So I could go to the code that I'm being requested to use. I could just go to the raw version to select it all and copy it all. Then I could go to this website. I could paste it. I didn't, oh, okay, there it goes. I could paste it on top of what it was saying there before. Now notice that the lines are a little long, so there's a little scroll bar here. And now if I want to run this Python code, I click on the green button, and on this side, it's going to print the output. And if I make changes here, like I put a 30 instead of 25, and I run again, it's going to print me a different thing. So if you cannot install Python, you can work with a thing like this perfectly well. I just think that for your professional development, it would be really helpful to learn to use it on your computer, because then you can actually put it on your curriculum that, hey, I know how to use Python. And I was just looking on Twitter earlier this morning. I posted it here, that for the first time in the past 20 years, Python is now the most popular programming language. There's most courses available, most code available online. Python has become more popular than C and Java, and I think it's high time. I think C is very valuable, and all true engineers should also know C. But Java was a thing of the 90s. Like it was really relevant when you guys were born, but like after that, kind of like, please, let's just let it go. So I'm happy about this change. I have similar thoughts about Visual Basic. I think that's a horribly bad idea. C++ is very good if you have to do high performance things, but most of us really don't have to. Stuff like JavaScript, you can't really avoid it yet, unfortunately, if you're in web development. I'm hoping that some good alternative is going to come and take over that too. SQL is kind of like the 90s way of doing databases, and PHP is it's an option if you need to make a website with some databases on it, but I think that's a bad idea. Assembly is never going to go away. I don't think C is ever going to go away, but for most purposes that we need, especially in engineering and computation, Python is a really solid choice, and it will be very helpful for you to become the kind of professional you need to be, and then to get a rewarding and well-paying job if you actually know Python. So I really, 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 really strongly recommend installing it and learning to use it. I will be hanging out on Discord until noon because I really want to help you guys if you have any trouble using Python. It's going to be very relevant for the rest of homework 4 and for some parts of homework 5. I would also like to remind you that the exam system is available for you at any time. So basically, if you're beginning to get curious on what's going to be happening in the final exam, we could go practice the final exam so we can look at what the questions are like. So here, when we're looking at the exam, come on, dollar signs. Okay, dollar signs went away. First question you can already answer. It's what's the order of the graph? What's the size of a graph? What's the density? What's the degree? There's an induced subgraph. All the first 5 questions, it's stuff we did last week. You should already know it. If you read the study material, you can also answer 6, 7, 8, 9. If you're too lazy to read the study material, I will explain those when we get to the part of practicing for the exam. Judging by last week, you should also be able to generalize to 10 and 11. And if you're too lazy to read the material, you can just wait. I think next homework, no, homework 5, we're going to do a spanning tree. Oh, there's a typo here. Let me go fix the typo. Then there is another topic we're going to be looking at in homework 5 that we haven't worked with yet, that are called binary trees. And with that stuff, we're going to be working from question 13 to question 18. So there's 6 points coming from binary trees. So you need to remember to be around for when we do homework 5. And then the last 2 problems have to do with properties of problems or properties of algorithms. And you can see here that the question 20 has a question of what's the worst case asymptotic complexity of a certain method. So you can start practicing for the exam. Let me go fix the typo in binary. Okay, fixed. So that's kind of our to-do list for the rest of the semester. When you're done with the first 5 homeworks, you can also start working on your project. So if you're eager to work on your project, you can just kind of like skip ahead on the homework. If you know how to use Python, it's pretty easy. I also have videos for the homework 5, but those are per question because that's a little bit longer. So we have 1 video for questions 1 and 2. Then we have 1 video for question 3 and 4. And then we have 1 video for the final question. So if you want to, you can skip ahead if this all feels really easy to you, but you're fine if you've done the first 2 questions of homework for today. That's exactly the goal. Let's go briefly check at how we're doing in terms of that goal. So if you have, at this point, a total of 34 points in homework, you're fine. You're doing perfect. If you know how to use Python, you can really just spend a little bit of time reading the study material and you're not going to be in any kind of trouble. If you're one of these people who haven't done homeworks 1 and 2 and who haven't really even started 3 and 4, please, please, please write something on the channel so me or someone else that we could help you. This is not a difficult thing, especially last week's homework. I gave you guys a program. I can help you use it. It's going to give you all of the 5 answers. So basically, everybody should be working on the 4th homework, but it's only 40% of people who are actually doing it. And another 40% of people haven't even started homework 3. So I'm a little bit worried about the people who are not working, but I know they're not here. So talking to them now doesn't really help because the people here are the people who are working well. So any questions about Python, homeworks 1, 2, 3, or the first 2 questions of homework 4, I will be on the channel until noon at your service. If this was confusing today, please join me again at noon when I will be doing these same things in Spanish. Thank you all. I'll give you the link to the recording in a bit, and I will also export it to YouTube for further viewing later on.